a constant term of 0, which it will have since Q, big Q and little q both have constant terms of 0. I guess we should also check that the first term is not going to be 0, which is also, I think, fairly obvious. Okay, so it's a group, and I won't mention that again, but just out of interest. So just for fun, and to get some idea about how these things work, we can actually work out the inverse of the one Riordan array we already know about, which is Pascal's triangle. So what is the inverse of Pascal's triangle? Normally we don't think of a triangle having an inverse, but of course if it's a matrix, written in a matrix form, an infinite lower triangle matrix, then it's going to have an inverse, as long as the determinant's not 0. So we just use the formula for Pascal's triangle Riordan array. We've got P is this and Q is this. So to get the inverse Q, we just rewrite x in terms of q, so q to the minus 1 is x over 1 plus x. Going back to our formula, it's 1 over p of q to the minus 1 of x and q to the minus 1 of x. So if we compute that, fairly straightforward, we end up with this as the Riordan array of the inverse Pascal triangle. We do the same thing as before. The only difference, now we've got plus signs instead of minus signs. If we do this exactly the same calculation, we just end up with an extra minus to the n minus k term, multiplying the binomial coefficients. So basically every other entry has a minus sign, and that's the inverse of Pascal's triangle. So now we come on to why Riordan arrays are useful. So this is really probably the most useful theorem, and allows you to generate a huge number of identities. Basically, g of x is a generating function for some sequence, and it could be any sequence you like on OEIS, which has a generating function. Then if you multiply this generating function coefficients by the first n terms of a Riordan array, then it turns out this is equal to the x to the n coefficient of this quantity here. This is actually fairly easy to prove. It's the one proof I think I'll do in this talk. First we need this result here, which is basically how to get, if you've got the generating function g and you've got a generating function q, how to compose g and q, what you end up with. This result here is fairly easy to see if you just multiply out the terms. The important thing is, which we have for Riordan array, is that this only works if the constant term of q to the qx is 0. Otherwise, you'll end up with infinite constant term. So that's actually basically why we have this restriction on Riordan arrays, that you need to have q0 equals 0. I should mention that the alternative definition, I've said this is the definition used in the online pre-true integer sequences and recent literature. The alternative definition you sometimes see is people sometimes add an extra x here and say it's p times x times q, all in brackets to the power k, in which case then you do have a q0. But this seems to be the most common definition now. But you just do have to be aware of that.
Michael, usually Q1 is not 0.
Yes. And for what's called a proper Riordan array, which we'll come on to a bit later, then Q1 definitely is not allowed to be 0. Yeah. Sorry, yes.
Okay, go ahead. Is the group commutative?
That's a good question. Commutative, is it commutative? I should have checked that, shouldn't I? Is multiplying lower triangular matrices commutative? It came to my mind to check that, so I can't actually remember. But yes, fair question.
Respond to the metric multiplication, right? So
Yes, I just can't remember if lower triangular matrices, I think they're not commutative in general when you multiply them.
It's too much to answer.
Yeah, okay, so I guess the answer in general is no. Yeah. Right, so yes, so we're proving this partial sum theorem. So to prove it, we'll start from the right-hand side and hope to get this in the end. So it's the coefficient of x to the n of this expression here, which we can now write in this way. We're summing over k, so we can take the px outside. So the px is already outside. We're just changing this g of q into this expression here. It's a sum over k. We're allowed to put this p of x inside. And then the second step is to notice that, well, we're only extracting the coefficient of x to the n. So we don't need to sum to infinity. We only need to sum up to n. Because remember, q of x has no constant term. It has a q1, which is q1 times x plus. If you raise that to the power k, you get x to the power k, and if you have k greater than n, you won't see it. Okay, so we can reduce this sum from 0 to infinity just to up to n, and then we have this expression. So the expression is very simple to prove, but remarkably useful. So let's actually just try using this expression, applying to the Riordan array we know about, Pascal's triangle. So, well, this thing here we already know is just n choose k, and we've got n choose k times any number in a sequence. Okay, so G is basically any number in your sequence. Could be Fibonacci numbers or Catalan numbers, whatever you like. And then this is equal to, so according to this, it's equal to the coefficient of x to the n of p, which is 1 over 1 minus x, times, and then the generating function for that series applied to q, which is x over 1 minus x. This is actually called Euler's transformation. It's known about, presumably, by Euler, or related to his work. So next, actually, let's try using that transformation on a particular example. So an example of a generating function, a very simple one with a finite number of terms, is just 1 plus x to the n. If we expand 1 plus x to the n, then we just get the binomial coefficients. Okay, it's 1 plus n choose 1 times x plus and so on. So the gk, so g0, g1 to up to gn, are just n choose k. So why do we choose that? Well, basically so that we get n choose k squared. So we can now work out what this sum here is equal to. So we just apply the formula. This is coefficient of x to the n of p, and then we've got g, so it's g of q. So g in this case is 1 plus x to the power n, and instead of x we've got q. So we have 1 plus q to the power n. Again, if we multiply this out, we end up with this, and if we do something similar before, use binomial expansion, it turns out that the answer is 2n choose n. So very simple to get that identity. We can do other things with this partial sum theorem. Things that, for other applications I'll talk about a bit later, things that you might want to calculate are the sum of a row in the Riordan array. So the sum of a row, how do we get that? Well, it's simply summing we only need to sum from k equals 0 to n, because then after that it stops. So that's simply, we're summing, keeping n constant, we're just summing along a row in the triangular matrix, lower triangular matrix. So to get that, we need to put gk, if we're going to use this theorem here, we need just to put gk equal 1. So we need the generating function such that we've got 1 plus x squared plus x cubed. All the coefficients of x to the n are 1. And that is a well-known generating function, simply 1 over 1 minus x. So we then use that. That's going to be, going back to our formula, it's p times g of q. So g of q, g is 1 minus over 1 minus x. We've got p, and where have we gone? Yeah. So we just end up with 1 over 1 minus q times p, which is this. Similarly, we can get the alternating row sums, where instead of having 1, we've got 1 alternating with k. The generating function for that is 1 over 1 plus x, same as before. And also we sometimes want the weighted row sums. Now we're going to change our g of k to be equal to k itself. This is also easy to get, the generating function of that. You actually get just by differentiating this one. Gives us this. So we just apply the same thing as before. It's p times g of q. And g of q, we just replace the x by q, and we end up with this expression here. So it's easy to calculate the all these things to do with Riordan arrays. We just get a generating function from the p's and q's and extract the coefficient of x to the n. There's a slightly more complicated one, which is obtained from a sort of modified version of the partial sum theorem, which will now show how we get. If we instead of considering the coefficient of x to the n of p times g of q, if we put an extra x here, then and see what we get another result. So we put an extra x here. We end up multiplying this by x. We get an extra x to the k here, and the same